Gonna have a quick little check-in to make sure Newton's first law, the lesson posted the other day, makes sense. You read through the PDF. If not, take a minute to read through this on your own, and I'll just talk you through what hopefully you got from when you read through it. The first little part in here is, especially with this distance learning, we're gonna have to use our imagination and think creatively. Maybe skills you don't necessarily think of associated with doing physics, but we'll have to use imagination. Picture how things would feel or look as we try and figure things out at a distance. Even if you're in classroom, I'd get you to use your imagination and think things through. Newton's first law, a lot of you have it memorized. Objects at rest tend to stay at rest. Objects in motion tend to stay in motion unless they are acted on by an unbalanced external force. It's an answer to the question, why do things move? They move because forces make them move. Galileo came up with inertia first. Inertia is basically an old word for resistance to change. So in chemistry, you might say some chemicals are inert. They don't want to change or react. In physics, we say objects have inertia. They don't want to change their motion unless there's these unbalanced external forces. The unbalanced part, basically, if we cut to the chase, it's kind of way down here. It's whether the forces cancel each other out or not. If forces cancel each other out, then the motion won't change. So if something's standing still and it's being pushed one way, so let's say it's this guy in the middle, let's say he's pushed one way, and at the same time he's pushed the other way, if those two forces are balanced, that means they cancel out. That means he's not really going to change his motion. It also applies if something was already moving. If something's moving forward and the forward force on it is the same as the backward force on it, then those two forces cancel out and it's not going to change its motion. So it'll keep moving forward. If the forward force on something were a little bit bigger than the backward force, then there's an unbalance and the forward force would make it go faster forward. If we put it in terms of this guy standing in the crowd, if the force in one direction is bigger than the force in the other direction, he's going to move in the direction of that bigger force. We'll get more to that in the next lesson. The next part of Newton's second law is the external part. To influence the motion of something, the force has to be outside. If you're sitting inside a car and pushing on it, you're not going to change the motion of the car. You have to be external to it. If you're standing on the ground and pushing on it, then you'll actually be able to change the motion of the car. Kind of a classic old school cartoon that I used to watch when I was a kid, the Wile E. Coyote and the Roadrunner. If you were to build something like this, the wind blowing on the fan, on the one hand, that would make the wind blowing on the sail. On the one hand, that would make the sail would make him want to move forward, but the action of blowing wind forward actually pushes the fan backward. We'll get more on that when we get to Newton's third law. But if everything's connected, the sail's connected to that coyote and the fan's connected to the coyote, this is an internal force. That's not going to change his motion. If you were to disconnect the sail, then the fan would make a move. Or if you were to disconnect the fan and just have wind blowing, that would make a move. But if he's got all three things connected, that's not going to make a move. Okay, the last little bit where we're really using our imagination. What does it feel like if your car accelerates forward quickly? Feels like you're pushed backward in your seat. There's something called whiplash. You can watch that little YouTube video there. Your headrest prevents your head from getting hurt. What if you come to a sudden stop? The car slowed down, but your inertia kept you going forward. So it feels like you're pushed forward, but really it was the car stopping underneath you. In cars, we put in seatbelts and airbags so you don't hurt your face whacking it off the dashboard or windshield or steering wheel. The bottom line is whatever you feel, whatever inertia causes you to feel, you're actually doing the opposite. A cool scenario is we can apply it to turning. If a car turns one way, you're going to feel pushed in the other way. If you're bored, you can look up something called centripetal motion. We're going to learn that in grade 12. And then the one that we don't like is if people call it centrifugal force. When people didn't understand circular motion and inertia, they thought that there's actually a force pushing you to the outside of the circle. But there's no new force. It's just your inertia makes you feel like you're going outside, when the car turns underneath you. That's really what I wanted to talk you through for this document. Email if you've got any questions, and see if you can do the check-in problem if you haven't yet.